This is section 8.5, dividing radical expressions. Recall the quotient property of radicals says that if nth root of a and nth root of b are real numbers and b is not equal to 0 and n is greater than or equal to 2 as an integer, then the nth root of a over b is equal to the nth root of a over the nth root of b. We can use the quotient property of radical expressions in reverse to simplify a fraction with radicals. Example 1. Simplify the following expressions by rewriting them as a single radical. Then try to simplify the fraction by finding the common factors in the numerator and denominator. So as the directions say, I'm just going to combine them into one. So this will become the square root of 72x cubed over 162x. Now 72 and 162, those can be reduced by 2. And then the x and x cubed can reduce. So we get square root of 36x squared over 81. And then taking the square roots, we get 6 absolute value of x all over 9. Part B, I'm just going to reduce. We can reduce by 3, so we get the square root of 25, and we can reduce a q to the 4th, over 36, square root of 36, which then becomes 5 absolute value of q squared over 6. Part 2, rationalizing the denominator. Rationalizing the denominator is the process of converting a fraction with a radical in the denominator to an equivalent fraction whose denominator is an integer. For our purposes, a fraction will not be considered simplified if the radicand contains a fraction. Specifically, a radical expression is considered simplified if there are no factors in the radicand have perfect powers of the index, no fractions in the radicand, and no radicals in the denominator of a fraction. To rationalize a denominator with a square root in the denominator, we use the property that the square root of a squared equals the square root of a times square root of a. So for 4 over the square root of 3, I'm going to multiply by the square root of 3. That way, the denominator becomes square root of 3 squared, which is just 3. So it's an integer. But remember, with fractions, whatever you do to the bottom, you must do to the top. And then 4 times square root of 3 is 4 square root of 3. And we get 4 square root of 3 divided by 3 as our final answer. So in general, if there's a single square root in the denominator, you just have to multiply by itself. So this will become the square root of 3 over the square root of 4 times 5. Notice how I'm simplifying the square root of 20 first. I always recommend to do that. So this becomes the square root of 3 over 2 square root of 5. And now I'm going to multiply by the square root of 5 over square root of 5. And we get square root of 15 over 2 times the square root of 5 squared, which is square root of 15 over 2 times 5, which is square root of 15 over 10. We can follow a similar process to rationalize higher index radicals. For example, to rationalize the denominator containing the cubed root of 5, we would need to multiply by the cubed root of 5 twice, because we would want the cubed root of 3 times in order to attain an integer denominator of 5. So example 3, 1 over the cubed root of 6. So I'm going to multiply by the cubed root of 6 times the cubed root of 6 over the cubed root of 6 times the cubed root of 6. So that becomes the cubed root of 36 all over the cubed root of 6 cubed, which is the cubed root of 36 all over 6. And just like in example 2, part B, I recommend simplifying if possible. So for part B, I'm going to notice that 8 is 2 cubed. So unfortunately, I can't simplify it. But this time, I don't want to multiply by the fourth root of 8x 3 times in order to get 4. But because the 2 is cubed, I want to multiply by the fourth root of 2 in order to get 4 2's. But I only have a single x, so then I would do the fourth root of x cubed in order to get 4x's. Whatever you do on the top, you have to do on the bottom. So this becomes 2 fourth root of 2x cubed on top, all over the fourth root of 2 to the fourth x to the fourth, which becomes 2 fourth root of 2x cubed all over 2 absolute value of x. To simplify a fraction when the denominator is a sum or difference with square roots, we use the product of conjugates pattern to rationalize the denominator. The products of conjugates pattern states that a minus b times a plus b is a squared minus b squared. The terms a minus b and a plus b are called conjugate pairs. Example 4. Simplify each expression. Square root of 3 over 1 square root of 5. So I have a difference of square roots in the bottom. So I'm going to multiply by the conjugate pair, which is 1 plus the square root of 5. So we get 3 plus 3 square root of 5 on top. And then using the difference of squares formula, we get 1 squared minus the square root of 5 squared on the bottom. So we get 3 plus 3 square root of 5 over 1 minus 5, which is 3 plus 3 square root of 5 over negative 4. Number 2, 5 square root of 2 over square root of 7 plus square root of 2. So again, I have a sum of square roots, so I'm going to multiply by the conjugate pair, which is square root of 7 minus square root of 2 on the top and bottom. So this becomes 5 square root of 14 minus 5 square root of 4 all over square root of 7 squared minus square root of 2 squared, which is 5 square root of 14 minus 5 times 2 over 7 minus 2. So we get 5 square root of 14 minus 10 all over 5, which then can be reduced to the square root of 14 minus 2. And that is it for section 8.5.